Hello everyone. In this video, we are going to learn about matrix factorization and how matrix factorization plays an important role in recommender systems. So if we see around ourselves what kind of media we consume, we use Netflix, we use Amazon, we use music apps, okay, and in a lot of which products we are recommended a lot of items. On Netflix we are recommended movies, on Amazon we are recommended different products. So behind all of this recommendation engine, if we see like what is going behind this recommendation system, then we will find then there's very important mathematical concept, that is matrix factorization, that is being used, and it is very interesting to learn about this matrix factorization. So in this video we will learn what is matrix factorization and how it helps us in recommender system. Okay, so let's dive in. So let's take the example of Netflix. Okay, so on Netflix, if you see, there are users and there are movies. Okay, users are the users who are like coming to Netflix to watch different kind of movies, web series, and Netflix as a platform, it has like a lot of items. These items are nothing but a lot of movies. So how does Netflix decide that how, like, which movies to recommend to which user? So behind the scene, there is a very important thing which it uses. It uses the rating of different user item uh, pairs, okay, and based on those ratings, it recommends the movies or web series to users. So we'll see it like in this video how these things work. So let's say we are on Netflix platform. Okay, so let's take the example of Netflix, and on Netflix different users are watching different movies. Okay, so we have users, and the users are watching different movies, and when they watch different movies they also provide rating to these movies. And let's say that a movie can be rated from 1 to 5. Okay, where 1 means very bad, okay, it was a very bad movie, and 5 means that it was excellent, okay, the user really liked that movie. So on the basis of this concept, user, movies and rating, what we can do is we can start storing these ratings of the users. Okay, we can start storing these ratings of the user in a matrix format. So matrix is nothing but a mathematical tool which helps us like in storing such kind of data and then perform maths over that stored data. So let's design a matrix for this use case. So let's assume that we have some matrix of this format. Okay, so we have a matrix where we have rows, okay, and we also have a lot of columns like this. Okay, now what will happen is the rows in this matrix, okay, they belong to users. So what we can say is that each row in this matrix is an individual user of this platform, and each column here is basically a particular movie on this platform. So the movies are the columns and the rows are the users. So what we can also write is, like, let's say this row belongs to user 1, this row belongs to user 2, this is user 3, this is user 4, this is user 5, and so on. Like, there will be so many users. Similarly, on the column side we can say that this column belongs to movie 1, this column belongs to movie 2, movie 3, movie 4, movie 5, and so on. Likewise, there will be so many movies. Now as the users start exploring different movies and they consume a lot of content on this platform, they start rating the movies. So let's say user 1 watched movie 3. Okay, user 1 watched movie 3 and they really liked it. So when they really liked it, they will rate it like 5. And user 1 also watched movie 5 but they didn't like it, so they rated it 1. Okay, similarly we can fill up this matrix with the ratings of different movies given by the users. So for user 2 also we can fill this matrix, like let's say 1, 2, 3, okay, 4, 5, 3, 2, 1 1. Okay, this is very random, this is not any real data, but just to illustrate that how this matrix works, we have users on the rows, we have movies on the columns, and then the cells, they are nothing but the ratings for a user and a movie pair. Okay, so this is how this matrix can be filled. Now coming to the question, like of real life, so we all know that Netflix is a very huge platform, and any live system out there, it will not just have these 5 rows and 5 columns. Okay, so if you talk about Netflix, okay, so there will be millions of users, and there will be like thousands of movies, or even more than that. So let's talk about this matrix. If we say that here m is the number of columns, okay, which represents nothing but number of movies, and okay, or let's say m is the number of rows here instead of like movies, so we can say like m is number of users, which is nothing but the rows of this matrix. Okay, and n is the number of movies, okay, which is nothing but the number of columns in this matrix. So if we talk about Netflix, then this number of users, okay, the number of users can be in millions. Okay, similarly, the number of movies, it can go more than 1,000, okay, or even more than that. I don't know, like I haven't explored all the movies or content which is there on the Netflix, and that is true for most of the users. So why I'm saying this is that because if you see this row, if you see this row for user 1, we only filled 2 columns, but we left all the other columns. So when we are leaving the columns, it means that the user has not explored that content yet. And that is true, because on Netflix a user cannot explore all the movies or web series. That is true. Okay, so what we do in that case, we can simply fill them by 0. Okay, now here one thing to note is that 0, okay, it does not mean 0 rating. Okay, because as we discussed that the rating only ranges from 1 to 5. Okay, so 0 does not mean that it is like extremely bad movie. 0 just means that user has not rated that movie yet. Okay, and why they have not rated the movie? Because they have not found that movie, because there are so many movies out there on Netflix. Similar thing applies for Amazon. You might not have explored all the products, or you might not have bought like all the products, so how will you rate all of those items on a platform, right? So because of that, we put 0 in all those places. So that is the thing about this matrix. So we can fill all other cells like 0, because there is no rating which exists for those cells. Okay, so this becomes our matrix. Now coming to this problem, there are a number of users on rows, and then on columns there are movies. Now once we have this matrix, how we can use it to recommend movies to users? Okay, so very naive idea is that okay, so very naive idea is that we can use similarity search. Okay, we can use similarity search. uh, so how will this work? So we have this matrix, and we can treat each of these rows as vector. Okay, so let's say u1, if we take just first row of this, okay, just this row, let's say we just take this one row. So this one row, we can call it user1 vector. Okay, so this becomes user1 vector. And similarly, you can take any other vector. Let's say we take u4, this is another vector. So every row here in this matrix is a vector. Now what this vector represents? This vector represents nothing but the rating the user has given to all the movies on this platform. Okay, so if you want to write this u1, let's say, okay, we want to write this u1 vector, then it will look like this: 0 0 5 0 1 0. Okay, this vector will look like this, and this vector just represents the rating for different movies on this platform. Okay, and remember this 0 means that it is not yet rated, and only the positive numbers here are the actual rating. So the idea is that every row can be represented as vector here, and if you have learnt about vectors, then you know like vectors have a direction when we plot them on a graph. So let's say geometrically this vector u1 looks like this, okay, and u4 looks like this, okay. And then let's take another user, let's take u2 user, and that u2 user looks something like this, okay, geometrically. So if we see this geometry, what we can infer from this geometry, we can infer that u1 and u4, these are the two users, and we have plotted these vectors here, and they are pointing almost in the same direction, okay, they are pointing almost in the same direction, not exactly in the same direction, but almost like they are like similar. The gap here is quite less, so we can say that they are quite similar. While if you see user 2, then user 2 is completely pointing to an opposite direction, okay. So this we can say like it is exactly opposite to user 1 and user 4. So this new information, how it helps us in recommendation. So we can say that, let's say user 4 likes a movie, which is like let's say user 4 likes movie 4, okay. User 4 rated movie 4 very high rating, let's say they rated it 5. So what we can say, if user 1 has not watched movie 4 m4, then what we can say is that let's recommend movie 4 to user 1, okay. That is the idea here. So the similarity search idea is a very naive idea. It just says that by the notion of these users as vectors, we can find the similarity among different users. For example, let's say user 1 logs in to the platform, then what we will do, we will do a similarity search for user 1 against all the users, and then we find, okay, user 1 is similar to user 4, and user 4 recently liked this movie, and user 1 has not liked that movie, or sorry, user 1 has not watched that movie. So what we can do is we can recommend that movie to user 1 also. Similarly, for other users also we can follow the same idea. So this is a very naive idea, like which we can use for recommendation, okay. So now this is also like the actual mathematics which will work if you are building a recommendation system, but it will start failing when we talk about real systems, because real systems are not like 5 by 5 metrics, okay. As we discussed, like we will have like millions of users, we'll have like thousands, 10,000s of like movies, or like lots of products on e-commerce portals. So this metrics calculation, it will start failing, okay. So let's see what will be the problem here. If we talk about the problem, so the problems will be like two-folded. The very first thing will be like the matrix size will grow, okay. It will be very huge matrix, okay. Now there will be two problems, like you will need very high computation, okay. You will need high computation. Why you will need high computation? Because what you are doing here, you are taking the dot product, okay. To find this similarity, let's say to find the similarity, we use cosine similarity, okay, which is nothing but it calculates the dot products, okay. So what will happen, like you will be calculating the dot product of one user against all the users present on the platform. Now there will be millions of users, and there will be like thousands of movies. So you can say like a single vector is having 1,000 dimension, and then you are doing the dot product of different like millions of users. So you can just assume like how much time it will take, how much computation power it will take to calculate all those dot products. And that is why I'm saying that in a real system, the metrics will be very huge, and because of that, you will have to do very high computation. Also, if you're following this metrics method, then you'll have to store this metric somewhere, right? Then only you'll be able to perform this computation. So before computation, you will have the problem of high storage, okay. You will have the problem of high storage. And then the second problem is related to the storage also, is that sparsity. Okay, so this matrix will be sparse matrix. And what do you mean by sparse matrix? Like there will be a lot of zeros. There will be lot of zeros in the matrix. And why there will be a lot of zeros? Because as we learned that any user, they cannot like watch or explore all the movies. Even if you consider the most unemployed person in this world who is just sitting all the day and just watching different movies on Netflix, they will not be able to consume all the movies, okay, in their lifetime. Like some movies are coming new, like some movies are going out, so there'll be like a lot of movies there, and every user cannot have there's ratings filled up for all the movies in the platform. So a lot of zeros will be present, which is the vectors will be sparse. And again, it doesn't mean it is not sensible actually, like that you're storing all those sparse vectors just to add up to your storage and then like increase the computation also. So we have these two problems which will arise because of this simple naive method. So what do we do? Like how do we do it like at the industry level? So that is where we introduce the concept of matrix factorization. Okay, so we have this concept of matrix factorization. Okay, now we learned about matrix, and factorization is also very like fairly simple mathematical concept. Like if I talk in a very like elementary level, then if you have a very large number, let's say 100, then you can factorize it. Like let's say you can write it at like 20 into 5, and that will be equal to 100. You can also write it into like 10 times 10, that will also give you the same number. Okay, so there are various ways of writing 100 by factorizing it into smaller numbers, and you will eventually get the final number as the same number. Okay, so this is the concept of factorization. In terms of matrix also, we factorize the matrix, because the problem which we just discussed is that the matrix is very huge. Okay, so the matrix is very huge. So just like this huge number can be factorized into smaller numbers, we will try to factorize this huge matrix. This huge matrix we can factorize into smaller matrices. Okay, we can factorize them into smaller matrices which are easier to deal with, okay, which are easier to like store and compute, and that is why we are factorizing. So this is a fairly simple mathematical concept which we are trying to use in recommendation system. Now, okay, we decided that okay, we will factorize, but how do we factorize? On what basis we factorize? We cannot just create any two like smaller matrices and then say that okay, these are the matrices which we are going to like use for our recommendation system. So there are different ways we can factorize, and before that I'll introduce some of the concepts which are useful here. So first of all, we'll talk about latent factor. Okay, so we'll talk about latent factor, and let me introduce latent factor by assigning it the symbol k here. So we'll see what is a latent factor. So we just discussed that we have a huge matrix, and then we are going to factorize it into smaller matrices. And I'll say that let's have this huge matrix, and let's call this matrix as R. Okay, R means it is a rating matrix, and it is the same matrix which we saw here. Okay, this is the rating matrix which we are storing. So this is the same rating matrix, and this has the dimension of m cross n, which means that we have m rows and we have n columns. Okay, this is m is user, n is for movies. Now this huge matrix we can factorize it in such a manner that we get two smaller matrices. So let's introduce two new matrices, and let's call them U and V transpose. Okay, so we have got two smaller matrices U and V. Now U looks something like this. Let's say this is just for illustration. Okay, and this is another matrix which is V transpose. So this is U matrix and this is like V transpose matrix. Okay, and the dimension of these matrices will be m cross k, and this will be k cross n. So if you notice this K is something which we introduced as latent factor. Okay, we are calling it latent factor. I'll explain it here what it is. Just now focus on this the matrices, like we have U and V transpose matrix. So this U matrix is having the dimension of M cross K, and V transpose is having the dimension of K cross N. So this K here, we can say like this K here is nothing but latent factor, and it is kind of like representative of some concept. Okay, so you can also call it a concept, or better, let's call it a hidden concept. Okay, now, why I'm calling it a hidden concept? Like, if we talk in general terms, like if we just think about the movies example, then there are like thousands of movies. Okay. Now, if you think like about Netflix also, if you have to go and browse the Netflix movie catalog, then Netflix does not like just list down all the movies like serial wise or alphabetically. It also has the concept of category of movies, right? Or we can call it genre. So different movies can be assigned different genre. Like there can be like romantic movies, there can be like historical movies, there can be like documentary movies, right? And it is much easier to deal with the genres instead of individual movies. So the genres are something which you can relate with this example here, where we are talking about hidden concept. Okay, so the goal is, if we just take the movie example, then the goal is that we have this rating matrix, which is a very huge matrix, and then we are factorizing it into two smaller matrices, where this K is nothing but, let's say, genre. Okay, or a concept or genre. So here this dimension, if you observe, it is like M cross K, and M is the number of users. So if we just closely see this, like if we can write like what the new matrices are, so let's say U matrix. Okay, this is having a dimension of M cross K, and M is nothing but number of users. Okay, and K is the number of concept here. So if we just say here that, let's say, K is, let's say, 2 here. Okay, let's say that K is equal to 2, then what we are saying is that this hidden concept in the case of movie example is nothing but genre. So we can say like, okay, somehow we created this factorization and we found that, okay, K is equal to 2, and we are saying that there are two categories: history and romance, which means that what we are saying through the new matrices is that each user now, instead of having n columns for n movies, they're now having k columns, and each column represents a genre. Like this one is for history and this one is for romance. Okay, similarly for movies, like if you see, we still have like n columns, which means like currently we have n movies, which is the same as the original n movies. But now, instead of like m rows for m users, now we have just k rows. And so we can say like each movie, like let's say this is movie 1. Okay, so the movie 1 is now having two components, and each component represents a concept. Okay, like there can be a movie which has like both history and romance concepts. A movie can be purely romantic, a movie can be purely historic. So that is the idea of these two new matrices. Okay, so that is what we are saying, that m users now they have like k concepts. Okay, now each user, instead of having n ratings, now they are having k concepts. Similarly, V is like for movie metrics, and we are saying like they have this dimension. Okay, so we have like n movies, and the n movies have like, each movie has k concept. So that is the idea of this latent factor. Now, how you will utilize the factorized matrices, okay, using this latent factor. So we'll see one example. Okay, so what we can write here is that this R rating matrix, now we factorized it like this. Okay, and the dimension of R is obviously m cross n, U has like m cross k, and we saw that V transpose as k cross n. So if you multiply these two matrices, you will get the same R matrix with m cross n dimensions. Okay, and that is why this math is like satisfying the equality sign. So it is all okay. And conceptually, I also explained you that what is the meaning of K. Now, how do we find K, or how do we factorize this matrix? That is a different concept to discuss. There are different methodologies like gradient descent, singular value decomposition, and there are so many methods which help us to calculate this K value. Now this K value, we are saying that they are hidden concept. We don't know what it is. Okay, here we like assumed just for understanding it that it can be genre like history and romance, but it can be anything. It is a learned parameter which we like learn when we train any model on this entire data set. Okay, but theoretically this is how you can understand it, that these are two new matrices which we learned, and K is a hidden concept. In case of movies, it is just genre. Okay, now let's take one example to better understand this concept. Let's say a user who is history lover. Okay, so what we can say is like this. Let's say this is a user and he is history lover. So we can write the vector for that user in our new matrix format, this format, where like we learned about that there are two concepts, K is equal to 2. So the dimension here will be 2. So this is how we can write it. Like this represents like the first element here represents history, and the second element here represents romance. So if we are saying that this user is history lover, okay, which means that they like more history movies rather than romance movies. So the history part here is 1 and the romance part here is 0. It can be like 0.8 sometimes if they like somewhat romantic movies. Okay, but this is how you can write the vectors in terms of new matrices. Now let's say how we will recommend movies to this user. Now let's say we have like two movies with us. Okay, let's say we have a movie called Troy. Okay, and let's write the vector for this movie. Let's write it like this. And since if you have watched Troy, it is a historical movie, so its history component will be 1 and its romance component will be 0, unless you assume that there was a lot of romance in this movie. But let's assume that this is the vector for Troy, and then we can take another movie example, which is Titanic. Okay, so Titanic, we can write the vector for Titanic like this, 0, 1, because Titanic is fairly a romantic movie, although it is historical as well. But for this example, let's take it simple. Let's categorize these two movies like this. This one is historical and this one is romantic. Now what we will do is we'll simply take the dot product of this user vector against this movies vector, and we'll get some value. Okay, so if we take, let's just call it u1. So u1 and the dot product of v1, and we'll also take u1 and dot product of v2. Okay, and if you take the dot product of u1 with v1, you will get 1, and for this one you will get 0. Okay, so you see, like if we take the dot product of user 1 with this Troy movie, you are getting 1, which means that we can recommend this Troy movie to the user. And that makes sense also because our user is history lover. So obviously the Troy movie will be recommended instead of the Titanic movie. If the user one was a romantic movie lover, then Titanic would have been recommended. And that is how the maths is working here. So how we did the dot product, because you see here this matrices which we like factorized. So here you are taking the dot product, which means like you can take the dot product of this row with this, and then you can get the final rating for that particular user for that particular movie. Okay, and how does this work behind the scene? Because we have like factorized the very like huge matrix where we were having like millions of users and thousands of columns for movies. Now that has been factorized to a smaller dimension K, which is nothing but a hidden concept, and we call it latent factor. And now if you see the dot product, they are much simpler. Okay, earlier it was one user vector, it had like thousands of columns. Now it is only having K columns. Okay, so that is the simplicity of this matrix factorization, and this is how it works out in the real like platforms. Now this is not how it will be done in the production workflow, that every time a user logs in, you will be doing the dot products for all the movies and then you will recommend. So in production workflow, it is a bit different, although it may not be same, but to just give you an idea like how you can build a production system using this concept. Okay, so first of all, you will retrieve the vector for the user. Let's call it active user. So let's assume that our active user is this. We will get its vector, and then we will take the dot product calculation. Okay, we'll do the dot product, and similarly, like we did the dot product here. So just like that, we'll do the dot product of the user vector with the movies vector. Okay, like with the latent factor as the dimension, and we'll not do the dot product for all the movies. We'll only do the dot product for the movies which the user has not watched, just to optimize the calculation. And then we will not recommend like all the movies, we will re-rank. Okay, we will re-rank again based on the dot product value which you will get. Here we got the absolute value like 1 and 0, but you might get 0.8, 0.5, something like that. And then based on the values which you have got, you will re-rank and you will only recommend top n items. Okay, maybe like top 10 movies, or like top 5 products, something like that you can recommend to your users. So this is how matrix factorization works, and this is how it is used in the actual recommender system. This is a very basic concept, because all basically all the like recommender system, they have this matrix factorization latent factor somewhere involved in the calculation. So this is very fundamental to learn like all the different concepts in recommender system. So in the next video we will be talking about different ways to calculate the hidden concept, that is latent factor k. So there are a lot of methods. We'll learn them one by one. So this is all for this video. If you like this video, you can like this video, and you can put your comments in the comment section if you have any questions or any feedback for this video.